Imagine an ocean that breathes poison. The horizon is a metallic glaze, the air above it heavy like a held breath, the surface slicked with bacterial films in purple and green. The water looks alive, but everything you know about life is wrong here. Waves roll in sluggish curls because the sea itself is thicker, warmer, crowded with invisible chemistry that steals the energy out of gills and lungs. The smell carries a hint of rotten eggs and hot stone. If you step to the edge, you would feel heat lifting off it the way heat lifts from a forge. The most terrifying ocean that ever existed did not gain that title because monsters cruised in it, though monsters came later. It earned it because the water itself became a weapon. To find it, follow the rock record to the boundary where the Permian ended and the Triassic began. There, in cliffs that once lay on seafloors, a thin, dark seam separates two worlds. Below it are reefs of sponges and corals and brachiopods that filled ancient shelves with architecture. Above it, the limestone loses its scaffolding. The first meters are often black shale glittered with pyrite, a mineral that grows as tiny raspberry-shaped framboids when seawater loses oxygen and sulfur rises to take its place. That blackness is a confession. For long stretches after the worst mass extinction in Earth history, the oceans did not just run low on oxygen. They went anoxic, and in places outright euxinic, laced with hydrogen sulfide. In such water, animals suffocate while microbes bloom, reefs collapse. Food webs do not disappear so much as lose the middle and top, and then the base thins. How do we know these waters were deadly? Lines of evidence lean together like a row of overturned boats. In the chemistry of the shales, the ratios of carbon and sulfur tell you that organic matter piled up faster than oxygen could digest it. Biomarkers, molecules that serve as fossils for single-celled life, include compounds made by green sulfur bacteria that only thrive in sunlit but oxygen-free water. That means the anoxic zone did not stay down deep. It rose to the level where light still penetrates, so the sea's redox line climbed toward the surface and sometimes reached it. Iron formations in some basins point to pulses of dissolved metals that only stay mobile when oxygen is scarce. Even the size of the pyrite framboids carries a signal, small and uniform when water is consistently depleted. Microbialites, bulbous mats of calcified bacteria, spread across carbonate platforms where coral gardens had been. If reefs are cities, those mats are the improvised shelters that appear after fire. And in the teeth of tiny eel-like creatures called conodonts, oxygen isotopes register sea surface temperatures near the equator that climbed above the comfort of most modern tropical seas. The ocean was hot and often stagnant. It was full of life that did not help the lives we are used to. Something must have gone first to push it there. The culprit sits like a continent-sized bruise in Siberia, a stack of flood basalts poured out over less than 1 million years. Those eruptions exhaled carbon dioxide, methane, and the aerosols and halogens that kneecap ozone chemistry. Carbon warmed the air and sea. Warming reduced the density contrast that drives deep water formation. When the conveyor belts of the ocean stall, the depths fall still. Still water keeps its breath. Oxygen declines and stays low. Erosion from new rainfall patterns washed nutrients into marginal seas and shelves, priming algal blooms that pulled what oxygen remained into respiration and decay. In some models, even the chemistry of the nitrogen cycle shifted, so that the gates controlling productivity stuck open at odd times and fed booms that died into black mud. On land, fossil spores of plants showed deformities that match damage from increased ultraviolet light, a sign that the sky's shield thinned. The story is not a single switch thrown once. It is a handful of dials turned past their normal range together, and once the ocean crossed a threshold, it preferred to stay where it was. Stand on a Triassic shoreline in your mind and look out. The worst of the die-off has passed, but the sea is still recovering in a way that looks like a dream. The nearshore bottom is carpeted with microbial mounds. A few bivalves with high tolerance for foul water dot the scene like buttons on a coat. The fish that return are small. Paleontologists call this the Lilliput effect, a shrinking of body sizes after ecological collapse. Predators do not disappear forever, but during the first returns they are modest, and they feed before the bottom waters slip back toward night. In many places there is a daily dance, a shallow layer at the surface oxygenated by wind and by algae and sunlight, and below it an old black breath that rises when the sun goes and winds fall. In that world, you survive by timing and by edges. This is terrifying because the rules that make seas generous are bent. Modern oceans trade waters between poles and equator, mix with storms, and borrow oxygen from the winter winds. They house deserts of blue water where life runs on empty, and they house shelves that turn sunlight into plankton that turn into everything else. The early Triassic Ocean worked, for stretches, like a lake cut off from its source. It took oxygen only at the surface and in narrow windows. In the interior, it made its own weather of chemistry and density. Imagine diving on a reef and hitting a layer that smells like matches and apple cores half rotted, the kind of smell that a marsh burps on a hot afternoon. Imagine that layer as miles wide and months long, and you begin to feel what lived here. It would be simple and pleasing to say that once the ocean settled, monsters arrived and fear now had teeth. The truth is messier and more interesting. The recovery was slow, and in that slowness, new engines evolved. The first big marine reptiles, ichthyosaurs, appeared as slender swimmers that looked halfway between lizards and tuna, their limbs becoming fins, their spines lengthening into flexible keels. Nothosaurs prowled shallow seas like sea lions, paddling with limbs and twisting long necks after fish. Ammonoids, the spiraled cephalopods, returned from their own bottleneck with small shells and then flourished, writing calendars of recovery into their whorls. By the Middle Triassic, the ocean that had been a hazard became a stage. Ichthyosaurs grew large and fast. Some species chased squid in bursts that snapped tails like thrown ropes. Others browsed shoals like swordfish, but with different tools. A reptile called Tanistropheus hunted with a neck so long and stiff that it looked like a fishing pole attached to a body, the head dangling into the water while the torso waded in shallows or on shore. The strangest inventions always sit in the middle of a recovery. Over tens of millions of years, the oceans reset. Circulation strengthened. Reefs reinvented themselves with new coral lineages and old sponges. Fish radiated into niches that did not exist before, and sharks explored new teeth as if testing blades in a kit. By the Jurassic, plesiosaurs and plesiosaurs ran two flavors of marine reptile apex. One wore a long neck and a small head, perhaps cruising high in the water to snatch fish and squid. The other wore a heavy skull and a short neck and did not cruise so much as ambush with a bite like a hinge trap. This sea would be terrifying to a small swimmer for reasons we recognize. It is also beautiful in its energy. You can chart currents by the distributions of big reptiles and by where certain plankton shells gather in rocks. The ocean, once toxic by chemistry, now carries fear in moving bodies. If you want spectacle, the Cretaceous obliges. In the western interior seaway, a warm inland ocean that sliced North America, mosasaurs learned to slip through schools of fish and strike with double-jointed jaws that could spread to swallow prey large and kicking. Long-bodied species carved through water like torpedoes, while heavier species bullied, ramming and ripping in ways we read from healed bite marks on bones and from stomach contents preserved by luck. Giant predatory fish like Xiphactinus cruised these waters with faces like knives. Sea turtles grew to lengths where their shells could serve as rafts for remoras in imagination, and for barnacles, in fact. If you swam here, your fear would not be of a breathless sea but of the wrong shadow. Every 100 yards of water housed a set of equations about speed, angle, and impulse. And yet, this is not the ocean that wins the title. Terrifying animals concentrate fear in a point and a moment. The Permian aftermath spread fear as a field. That field ebbed in the Triassic and was replaced by episodes rather than an era. In the Jurassic and Cretaceous, there were oceanic anoxic events, bursts when large regions of the deep again went oxygen poor, and black shales accumulated on the seafloor beneath stratified nutrient-heavy water. They left signatures of carbon cycling gone strange, and their layers hold the fossils of plankton that bloomed and died and fell like snow you cannot shovel. But circulation returned after each event. Reefs persisted, fish swam their highways, predators raised their young at ledges, and could depend on a kind of weather in the sea. Terrifying is not a moment. It is a habit, and the early Triassic Ocean had that habit. What is hardest to imagine in that time is the quiet. Secure food webs create layers of noise, the fret of shrimp, the buzz of fish, the chuff of whales. The chemistry of an anoxic sea narrows the band of life that makes such noise. Microbial films do not crackle. Green sulfur bacteria would have made the surface glare in colors, but their work is silent. Bivalve beds whisper. Small fish flitter and snap, and their predators learn to listen. The most terrifying ocean is an ocean that refuses you. An oxygen drink the way a desert refuses you water. It is an ocean that turns predators into accountants, weighing when to risk a dive into a dark lair for a lurking shoal, and when to stay at the top and chase insects. It is an ocean that draws its own horizons inside itself. The fossils of that world are both humble and profound. Shelves show the absence of reefs as a gap that lasted millions of years. A reef hiatus that tells you not just who died, but who could not rebuild under those skies and currents. The return of reefs in the Middle Triassic is a celebration written in stone, a pointillist spread of corals and sponges stitching together surfaces that waves like to break. Scattered through those rocks are odd reefs built by microbes and by bivalves that learn to partner with bacteria in their gills for a living, taking chemical energy straight from seawater the way modern shellfish thrive at vents. This is an ocean learning to work different levers. When oxygen is low, you borrow chemistry. When temperature is high, you borrow time. Even the shell shapes tell the story. Ammonoids shrank, then diversified into coils that looked like ropes, discs, and helixes, a carnival of forms. Some of that decoration is fashion in evolution, signaling and compromise. Some of it is hydrodynamics, balance and center of mass. The smallest shells, abundant right after the boundary, are not only a record of youth, they are a record of a world where energy ran thin and small bodies returned investment faster. As oxygen climbed, shells fattened. Bodies bought time again. Perhaps the hardest thing to accept is that terror on this scale arrives by reinforcement, not surprise. The eruptions did not have to be exceptional in each individual pulse. What mattered was their persistence and the sensitivity of a coupled system. A little warming changes winds. Changed winds move rains. Rains grind minerals and feed rivers with phosphorus and nitrogen. Those nutrients feed algae that bloom in seawater that is already warmer and stratified. The bloom dies, falls, rots, and removes oxygen. Without oxygen to buffer reduced chemicals, sulfur takes a larger role. If hydrogen sulfide accumulates, it leaks up. In shallow places, it can touch light. Bacteria that love sulfide and light expand and add their biomass to the rain. The cycle runs. Once locked in, it takes negative feedbacks and time to push back. The terrifying ocean is terrifying because it is rational. It is a series of next steps that make sense. When the lock finally loosened, it did so unevenly. Some basins returned to blue water sooner than others. Some shelves recovered quickly with sponges and then corals. Others stayed matted in microbial felt. Predator guilds rebuilt where prey returned. In those basins, the shadows sharpened again. Fossil fish scales pile thick in some layers, the confetti of shoal lives. Shark teeth rest like seeds in others. Ichthyosaurs rose to giant size and some carried embryos, living their entire lives at sea and giving birth there. Nothosaurs seeded the top to plesiosaurs and to forms that no one would guess if they did not hold the bones. The sea reinvented fear as actors. By the late Triassic, the ocean you would recognize from a nature film had returned. Turtles, fish, marine reptiles, ammonoids, and early squid paced the seasons and the fronts. Storms tore shelves and mixed layers deeply. Upwelling returned to margins and brought cold, rich water to sunlit surfaces, feeding plankton blooms that built everything above them. Not every basin was the same. None of them were the long breath of a poison sea. If you swam, then your fear once again had eyes. The ocean itself, as a body, had relaxed its grip. It is tempting to leave the terrifying ocean as a story told about the worst day the sea ever had. The better ending is to read it as a lesson in thresholds. The Earth system plays by rules, and one of those rules is that parts of the system love their current states. Oceans are layered by temperature and salt. Mix them and they resist, unless you push hard. Push in the other direction, and the resistance can hold you in place for too long. We live after modern oceans learn to breathe through ice ages and warm periods, through the closing and opening of seaways, through the rise and fall of mountain ranges. We also live while adding carbon to the air faster than some past pulses, while warming surface waters and intensifying rainfall in some places and drought in others, while pushing nutrients off fields and into coasts. Dead zones bloom today in summer where rivers meet the sea. They are local and seasonal compared to an entire basin's slow suffocation. They rhyme with the past. If you could stand again on that Triassic shore and look out, you would see that the terror was not a permanent feature. The sun still set into a line, it turned to gold. Clouds still lifted from the horizon after storms and threw rain like a veil. Birds did not yet exist, but pterosaurs learned to skim, and insects stitched the air. In time, shoals would turn the surface into silver cloth again, In deeper time, whales would come. In our time, instruments listen for the same signals ancient rocks recorded, the whispers of oxygen rising and falling with season and storm. The most terrifying ocean that ever existed is gone, along with the architecture of the world that made it. Its traces remain in the chemistry of shales, in the framboids sparkled like beads, in the thinness of shells after the event, in the microbial domes built where reefs had been. The ocean has two talents that look like magic from the shore. It remembers, and it forgets. It remembers in its heat and salt, in deep waters that take centuries to trade places with surface, in the shells of plankton that snow to the bottom carrying patterns of light and temperature in their chemistry. It forgets every time wind lifts and breaks its surface, every time a storm shakes a basin from top to bottom, every time a current shears and recombines. Terrifying arrived when memory outlasted forgetting for too long, when the deep kept a record of breathlessness that the top could not write over. Terrifying left when time and energy wrote a new story. To walk a modern cliff and run your fingers across the seam that marks that ancient change is to touch the edge of an alien sea. Below your hand, an older world shone with reefs. Above it, the surface became a lens for purple light, made by bacteria at the top of death. Above that, shells thicken, bodies grow, predators return, currents quicken, and reefs knit stone out of living tissue. Terror is not the star of the story. Change is. The ocean has more ways to be itself than we imagine, and one of them, once, made the water breathless. Knowing that, we can look at our own water with sharper eyes. We can celebrate the shocks of blue that still turn upwelling and sunlight into fish, and we can read with care the places where summer brings a black breath to the bottom. We owe our awe to seas that work. We owe our attention to the fact that they have not always